Here's the last section having to do with the applications of derivatives in chapter 4. The idea of related rates. Um, Here's an idea. Imagine a sphere that's being inflated. Its radius is changing, and maybe the radius is predictable as a function of t. The volume is changing, and the volume of the sphere is predictable as a function of time. Can we find out how the rate of change in the volume is related to the rate of change in the radius? So let's say we start with something that we know, that the volume of a sphere is 4/3 pi r cubed, for example. Let's say we do something to both sides of the equation, and that is we're going to take the derivative with respect to t. Now there are no t's, there are no variables of time that you can see in the equation, but I just said volume is a function of time. Radius is a function of time. Therefore, when I take the derivative of v with respect to time, I get dv dt. I get 4/3 pi, which constant I set aside. And now I'm going to take the derivative of r cubed with respect to time. Bring the power down, keep the inside the same, reduce the power by 1. Notice I'm using the language of a chain rule here, and take the derivative of the inside. And that derivative of the inside is dr dt. To summarize, how does the volume change with respect to time? It's 4 pi r squared times dr dt, how the radius changes with respect to time. No, that's so much fun. Let's do that again. Let's assume that r and h are the radius and the height of a cone are differentiable functions of t. Let v be the volume of the cone. Let's talk about, of course, the fact that we know that v is equal to 1/3 pi r squared h. Imagine that I take the derivative with respect to time of both sides of that equation. And what happens next? Well, I certainly get dv dt. I certainly have a constant that can get pulled out. What am I taking the derivative of with respect to time? Looks like something that's going to be related to a product rule. 1/3 pi times first r squared times the derivative of the second, dh dt, plus the second, h, times the derivative of the first, 2r, bring the power down, reduce it by 1, keep the inside the same, derivative of the inside, dr dt. And there we have it, a function or a relationship between the volume of the cone and how r and h are changing. And we call these ideas related rates. Now, this particular set of problems is going to be interesting because we're going to have so many different situations. And one of the key elements of everything that we do is finding the equation that we're going to take the derivative with respect to t. So we're going to have to understand the problem. We're going to have to say, well, what kind of mathematical model is going on? Let's find the equation that we're actually going to take the derivative of with respect to time, and then substitute the values that we know about in the problem. So interpret the solution. Let's see if we can see this play out. So the hot air balloon is rising straight up from a level field tracked by a rangefinder, which is 500 feet from the liftoff point. So here's where the rangefinder is. Here's 500 feet. And here's the balloon, the hot air balloon. Here we go. and the hot air balloon is rising. Kind of looks more like a light bulb, right? There we go. At the moment the rangefinder's elevation is pi over 4. Okay, that means there's a changing, there's a angle that's changing. Let's call that angle theta because it's changing, it's variable. The angle is increasing at a rate of 0.14 radians per minute. Let me write that down, but in symbols. The rate of change of theta with respect to time when theta is pi over 4 is 0.14 radians per minute. Question is, how fast is the balloon rising at that moment? Well, we have, I won't use X there, I'll use Y. Y is the height. It's varying, it's changing, okay? Do we have the ability to write an equation which tie together our two variables, theta and Y? See, Y and 500 make up a ratio. Sure seems to me that maybe tangent of theta is equal to Y over 500. Or maybe I want to rewrite this as 500 tangent theta is equal to Y. All right, let's go ahead. Let's take the derivative with respect to t of both sides of that equation. And I'm going to get 500 times, what is that, secant squared theta times chain rule d theta dt is equal to dy dt. Okay, so I've got an equation. Now, can I plug in something that I know? And that is that 500 times the secant squared of pi over 4 times d theta dt. Oh, that's our 0.14 is equal to dy dt. So we plugged in the rate of change in the angle, we plugged in the angle, and now let's just do some quick calculations. 1 root 2 pi over 4, and secant is hypotenuse over adjacent. So this is going to be 500 times root 2 squared times, and I'll write this as 14 over 100 just to make it a little bit easier to work with. So this is 500 times 2 times 14, and the hundreds cancel. So 5 times 2 times 14. That's 10 times 14. 140 is what dy dt is equal to, and it has going to have units, and that is that it's feet per minute. And it's appropriate to make sure that we have the right units there. All right? Sound good? Great. Let's go on to another one. Every problem here is going to feel a little different. Police cruiser is approaching a right-angled intersection from the north. I get my intersection, and here's the police. And it's heading south. It's chasing a speeding car. Let's call that S. It's turned the corner and is moving straight east. Speeding car moving that way. Okay. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles east of the intersection, police determine with radar that the distance between them is increasing at 20 miles per hour. Let's say the distance between them, let's call this Z, because I'm going to call this X and I'm going to call this Y. And let's change this statement. into something in symbols. Are we ready? And that is the rate of change is 20 miles an hour. dz dt equals to 20 when x, which is the speeding car, is 0.8 and y, the police cruiser, is 0.6. So I've taken all that sentence and I have converted it into a statement about a rate of change. If the cruiser is moving at 60 miles an hour, what's the speed of the car? Okay. Well, let's write down, what is it, what's being asked of us in, what's being asked of us in that statement? See if we can convert that. What is dx dt when x is 0.8, y is 0.6? That's what's being asked. Okay, oh, and we're told one other thing. The cruiser is moving 60 miles an hour. That is saying that dy dt is 60? No, negative 60. This value of y is getting smaller and smaller and smaller, so it's got to be a negative rate of change. Our last trick here is that we are going to write an equation that ties these variables together. How about that x squared plus y squared is equal to z squared? So let's take that equation that relates x, y, and z. Let's take the derivative with respect to t of both sides. And we get 2x dx dt, that chain rule, 2y dy dt, there's the other chain rule, is equal to 2z dz dt. And I can take my red marker and I'll just divide everything by 2, nice and easy. Let's plug in what we know. We know that x is 0.8. We know, we're actually not trying to find, nope, yep, x is 0.8. We don't know what dx dt is, so that remains unknown, plus y, which is 0.6, times what dy dt is, which is negative 60, is equal to z. Wait, do we know what z is? Well, I can use Pythagorean theorem back here and say, hey, 0.8 squared plus 0.6 squared is equal to z squared. 0.64 plus 0.36, that's 1.00. Z must be equal to 1. Illustrating that, again, mathematicians are lazy and they must use 3, 4, 5 triangles wherever they can. So z is 1, and dz dt, we said, is 20. And that car is getting further away and is increasing. So now all we have to do is have to solve for x dx dt. So I've got, I'm going to write that as 8/10 plus 6/10 times negative 60 is equal to 20. Let's multiply everything. Oh, sorry, I forgot the dx dt. Let's multiply everything by 10. So I get 8 dx dt plus the 10 goes away, so it'd be minus 360 is equal to 20. Let's take the 200. Let's add 360 to both sides, and I get 560 divide by 8. I get dx dt is equal to 70. And our everything's in miles and everything's in hours. So that speeding car is moving at 70 miles per hour. Okay, let's do another example. And again, everything is different. In this one, we've got a conical tank. It's a cone down like an ice cream cone. And water runs into the conical tank at 9 cubic meters per minute. Let me write that down as a fact. The rate of change in the volume is positive 9. Okay, its height is 10 feet and its base radius is 5 feet. How fast is the level rising? How fast is the level rising? What is the rate of change in height with respect to t when h is 6? That's our question mark. So we've got a v, we got an h. Our trick is going to be to find a relationship between v and h. Well, we know about the volume of a cone, 1/3 pi r squared h. I have a v, I have an h. It'd be nice if I could get rid of that r. Well, it just so happens that when you have a tank filled with water, that water makes a right or a triangle, which is similar to, I'm going to red marker there, which is similar to a triangle that for the entire tank. In other words, this R and this H ratio has got to be similar to the ratio of the height of the entire tank, 10, to the radius of that tank, which is 2.5. Oh, base radius is 5. I wrote it as a diameter. Sorry. All right. So we've got this similar triangle, which is right here. And that triangle and the blue triangle are similar. So the ratio of the height of the water to the radius of the water, radius over height, has got to be similar to the overall height of the tank to its radius. And I can see here, I got this mixed up. This is a base radius. So this is 5 going here. So in other words, R is equal to 1/2 H. Meaning I can go back to here, and every place I see an R, I can replace it with H over 2. So what do we get here? D is equal to 1/3 pi. What would that be? H cubed over 4, or pi over 12 H cubed. Let's take the derivative with respect to t of both sides of that equation. And we get that dv dt is equal to pi over 12 times 3h squared dh dt. What do we know? We know that volume is 9. And we want to know how fast is the water level raising when it's 6 feet deep. So we're going to say that pi over 12 times 3 times 6 squared is dh dt. See, 9, see, it's 70, 36 squared is, 6 squared is 36 times, that's 3 times 36. 3 times 30 is 9, it's like 108 over 12 times pi dh dt. Pretty sure that 12 goes evenly into 108. about 9 times? 9 times 12 is 8, carry the 1. Yep. So this is 9 is equal to 9 pi dH dt. Again, mathematicians being very, very lazy. So that means that dH dt is equal to 1 over pi. We need units of measurement. That'd be feet is our measurement of distance, and minutes is our measurement of time. All right. Last problem, I think. Yep. The ladder problem. It's a classic. A 10-foot ladder leans against the wall. So we know that the ladder is 10 feet tall. The base of the ladder is being pulled away. So this distance x is changing, is varying, and it's being pulled away. So dx dt is 2 feet per second. Right? How fast is the ladder moving? The top of the ladder moving? Well, that means the height of the ladder is changing as the base gets moved on. We want to know what is dy dt when x is 6. Oh, by the way, if x is 6, the 3, 4, 5 triangle means that y must be 8. That's what's being asked. What's the equation that ties our variables together again? X squared plus y squared is equal to 10 squared. Derivative with respect to t of both sides of the equation. Derivative of a constant is 0. And here I've got 2x dx dt plus 2y dy dt. Divide everything by 2. Those go away. Plug in what we know. X is 6. Dx dt is 2. Y is known. It's 8. Dy dt is unknown. Let's solve for dy dt. How about 8 dy dt is equal to -12. That means dy dt is equal to -12 over 8, which is 1.5 feet per second. And there we go.